So far, we have considered only structures that feature horizontal and vertical elements. Structures that feature inclined members can undergo more complex movements at collapse. To handle these more complex kinematics, we must use a method called instantaneous centers of rotations. Prior to using this method, we need to consider some additional elementary mechanisms. Qualitatively, the following elementary mechanisms exist for frame structures. For regular portal frames, shown in figure 1 here, we have the sway and beam mechanisms. For portal frames that feature inclined members, generally, we also have a sway mechanism and two independent beam mechanisms, beam 1 and beam 2, and a new type of mechanism called a gable mechanism, which is like a combined mechanism, except that this is an elementary mechanism. The method of instantaneous centers of rotation is used to evaluate the complex kinematics of structures that feature inclined members. The point of this procedure is essentially to determine the displacements delta and angles of rotation. The method relies upon tracking the rigid body motion of a segment of the structure through an angle and then relating all other rotations in the structure to this angle. In the diagram shown, we have supposed that there are plastic hinges at A, C, D, and E. From this, we're able to construct three rigid bodies. The first one is A, B, and C, so we can see that the segment A, B, and C can, if the rest of the structure was removed, move as a rigid body. The next rigid body is C and D, and the final rigid body is D and E. The value IC is the instantaneous center of rotation on the imaginary body C, IC, and D. What we have done in this case is we have passed a dashed line through the first point A and C simultaneously and kept it going, and then we have also passed a dotted line through E and D. In this case, the instantaneous center of rotation is where these two lines cross. The height of the structure comprises of two segments, H1 for the vertical bit and H2 for the bit that features the inclined members. The final height, H3, is the height at which the instantaneous center of rotation lies above point C. As we've said before, the rigid body C, ICD, this rigid body, rotates through an angle theta. In order to show this motion, we will track this deformation using red lines. Firstly, we move the rigid body through the angle theta. And similarly, at this location. So this then allows the rigid body C and D to swing through the angle theta. Then we need to connect all of the other parts of the structure up to this displaced rigid body. So rigid body A, B, and C has now moved. And similarly, rigid body D and E has also moved. We can also draw additional dotted lines to help track the angles of rotation at other locations in the structure. We can assume that the angle of rotation at A is given by a new angle, which we'll call phi. The angle of rotation at the instantaneous center of rotation is given by theta, and the angle of rotation now at E is given by a new angle, which we'll call alpha. At point D, we have a horizontal displacement, delta D, comma h, and at point C, we have a vertical displacement, delta C, comma v, and as this is a complex mechanism, we have a horizontal component as well, which we will call delta C, comma h. We now attempt to relate the displacements and angles in the following way. Delta D, comma h is equal to h1 times by alpha. We can see this here. It's the height of the member times by its angle of rotation. And similarly, in terms of theta, it's equal to h1 plus h2 times by theta. We can see that here. h1 and h2 times by theta will give us this equivalent angle. As a result of this, we can then say that alpha is equal to h1 plus h2 over h1 times by theta. For delta C, comma v, we have L1 times by phi, which is equal to L2 times by theta. So that means then that phi is equal to L2 over L1 times by theta. Delta C, comma h is equal to h3 times by theta, which is also equal to h1 plus h2 times by phi. So phi can also be defined as h3 over h1 plus h2 times by theta. The quantity h3 at the moment hasn't been defined by the geometry of the structure, and this needs to be defined using similar triangles. So we do know that we can construct a triangle inside the structure, drawing a diagonal line from A to C. We know then that the base of this, as defined by the structural geometry, is given by L1, and the height of it is given by H1 and H2. We can then, using the same geometry, construct a larger triangle that also features H3 in its definition. And within that, we can see the base of the small triangle at the top is given by L2, which we know. Comparing these triangles then, triangle 1, H1 plus H2 over L1 is equal to H3 over L2. So H3 is then simply given by H1 plus H2 divided by L2 over L1. Having done this, we can now go on and proceed to perform virtual work as usual, as all of the displacements and rotation angles have been defined. Just as a correction, the displacement delta comma h, it was said that it was equal to h1 and h2. Looking at the diagram, it is actually equal to h2 plus h3 times by the angle theta. With these complex collapse mechanisms, they often feature loading in both the horizontal and vertical directions. And as a result, you need to be able to understand how these loads interact and how a safe region of load interaction can be defined. Suppose we have the following collapse mechanisms for a structure. Collapse mechanism 1, which is a beam. Collapse mechanism 2, which is a sway. And collapse mechanism 3, which is a combined mechanism. Imagine now that we have conducted an analysis and we have concluded that, firstly, W has a value of 4 for collapse mechanism 1. For collapse mechanism 2, H is equal to 3. And for collapse mechanism 3, we found that W is equal to minus H. From this, we can identify combinations of H and W that are either safe or unsafe by constructing a load interaction diagram. To do this, we simply plot these values on two axes of W and H. In this case, H has been put on the horizontal axis and W on the vertical axis. We've said that W is equal to 4. So this is for mechanism 1. We've also said that H is equal to 3. This is for the second mechanism. And finally, we said that W is equal to minus H. This is for mechanism 3. The safe region, therefore, can be identified as the region that is bounded by all three of these mechanisms. Any combination of H and W that lies within this region can be considered a safe combination of loads.